Alors, bonjour tout le monde. Bienvenue à cet avant-dernier séminaire d'astronomie et d'astrophysique du CRAC pour l'année 2024. Aujourd'hui, je suis très heureux de vous introduire Pieter Schillemans, donc qui est en direct avec nous de la Belgique. Alors, j'ai eu le privilège de rencontrer Pieter pendant mon stage de recherche financé par le CRAC justement l'été dernier à Louvain. Peter est en fait dans sa deuxième année de doctorat dans le groupe du professeur Jan Sundqvist. Se spécialise en ce moment dans la modélisation hydrodynamique de vents d'étoiles LBV, un type d'étoiles massives assez rare, plus rare et plus extrême encore que les Wolf-Rayet qui sont chers à mon cœur. Alors, je suis très heureux de vous introduire et de vous présenter ce chercheur sur un domaine assez niché et surtout qui fait de la recherche à la fine pointe de la technologie. Alors, Peter a précédemment complété une maîtrise aussi dans le groupe du professeur Jan Sundqvist, donc aussi sur les étoiles LBV, donc il a quand même une bonne expérience, un des leaders, un des chercheurs en fait les plus spécialisés, je pense, dans le domaine déjà au monde. Peter avait aussi précédemment complété un master's et un bachelor's et un master's en astrophysique à l'université de Anvers, ou Antwerp en anglais, en astérosismologie, donc des étoiles RR Lyrae, donc des étoiles de plus faible masse pulsantes. Donc Peter est passé des étoiles pulsantes de faible masse, surtout en physique des particules, aux étoiles les plus massives pulsantes aussi, éruptives dans le spectre de masse. Alors, un parcours vraiment très intéressant pour Peter. Et écoutez, sans plus tarder, je vais le laisser nous faire sa présentation sur les simulations 2D de LBV-like atmospheres and run flow. Peter, thank you for being here and take it away.
Thank you. Yeah, like Guillaume said, I'm Pieter, second year PhD. All in English, I'm afraid. My French is definitely not good enough to do this in French. About these 14 months for me, about two simulations of these LBV and LBV-like outflows that I've been running. Now, there's a lot of jargon, of course, in this title, but I think it best to just start right at the beginning at our agenda. So on the agenda today, I will just start with introducing massive stars and LBVs. I understood that this is not a focus for many in this group. I will also go over the basics of RHD simulations, and so radiation-hydrodynamic simulations. I will then go into my own simulation setup, and then I will discuss two 2D simulations and their implications. So let's start with the introduction. So just at the very top level, massive stars, what I mean with this, these are stars that have masses that are starting from 8 solar masses and higher. They have convective interiors and radiative envelopes, and they end their lives as compact objects, so either as a neutron star or as a black hole. Now, these stars are extremely important for astrophysics, important for chemical enrichment, and so they synthesize heavier elements in during their lifetime. They're also important for galactic evolution, for example, this chemical enrichment, or their ionizing radiation, their supernovae. And of course, since they if they end up as black holes, then anything you have to do, you want to do with black holes, such as gravitational wave sources, you also need a massive star somewhere in the mix there. And at every point in their lifetime, their mass is basically their most important aspect of these stars. And they lose quite a lot of mass over their lifetimes. Now, the rates at which they lose this, they are, of course, very crucial if you want to do anything of evolution or predictive modeling, but they're very non-trivial to get. Now, one caveat of what I'll be doing today, massive stars are overwhelmingly, some 70%, they live in binary systems. However, I will today not be binaries. I will just look at them as if they were still LBV stage. Let's just go a very classical view massive star, single star. So just starting at gas cloud, falling in, and then becoming eventually a main sequence star. And if it's very massive, let's say some 60 solar masses in the main sequence phase, then eventually we'll go to a Wolf-Rayet star with, let's say, for example, 20, 25 solar masses. So in between, we need to lose a lot of mass. And this is then where the luminous blue variable stage, or the LBV stage, comes in. And because these stars, they seem a lot of mass. And yeah, so after, and yeah, so that is what you need then to go to the Wolf-Rayet phase. And then eventually, of course, supernova, and then end up in either a black hole or a neutron star, depending on mass.
Peter,
Now, what do I mean
just
with
a
yeah?
just a quick thing. We're having some signal problems. I think it's coming from your end. Do you think you could just maybe deactivate your camera, see if it frees up more
Oh,
en passant? Sorry, I don't know. Forget the English word for it.
yeah, I will definitely try this. I hope so.
Yeah, it's okay. I think right now it's you're back.
Okay, that's good. Thanks for the notice. So, with their star went some 40 solar masses up to easily 100 solar mass. Effective temperatures of anywhere between 6 and perhaps 36,000 Kelvin. Notice if it's 6,000 Kelvin, it's not really blue anymore. So luminous blue variables are not necessarily blue. They are, however, very luminous, luminosities of 200,000 to 3 million solar luminosities. And they are exceedingly rare. So there's only some 40 to 50 cases confirmed, which some 100 candidates still. But they're rare for a couple of reasons. So for example, of course, these are the very, very massive stars, so there's just not a lot of them. Then this LBV stage in the classical overview, it only takes around 10 to 20,000 years. So that again makes detection quite hard. And the third reason is there's no really single defining like spectroscopic feature or temperature class or so. You really only know if you're dealing with a luminous blue variable if you have spectroscopic or photometric variability. And this is quite difficult to obtain sometimes, this confirmation. So there's two classes of luminous blue variables. You've got the Doradus, and this is the most normal class of LBV. These show periodic movement between two places in the HR diagram. Now this movement takes several years to decades, which then again harks back to the former point, where if you need to see this variability, you need to observe them for several years or perhaps even going to decades. But yeah, so there they go between these two stages. So on the one end, you've got the quiescent stage, where they're slightly hotter, so 12,000 to 36,000 Kelvin, and they have inferred mass loss rates, observationally inferred, of about 10 to the minus 5 and 10 to the minus 4 solar masses per year. Now they live in these two gray strips on the side. They live in the left one. Now, 10 to the minus 5 to the minus 4, that perhaps does not really sound like a lot, but for example, the sun at this point loses 10 to the minus 14th solar masses per year. So these lose a lot of mass. And then in their outburst phase, which then is their this strip on the right, they have a quite low effective temperatures, 6 to 8,000, and their mass loss increases even more to, let's say, again, inferred mass loss rates of 10 to the minus 3 solar masses per year. And they move between these two stages, sometimes several times, with, well, in principle, it's a constant luminosity, or it was thought to be a constant luminosity, but that is being called into question. So yeah, there's still a lot of unknowns about these stars. The other class of LBVs are the Eta Carina, or the giant eruptions. These are one-off events, so again, it's quite difficult to then really confirm them, because some LBVs might not have blown up, or so that's quite difficult then. And yeah, so these are even more extreme. So for example, Eta Carina itself, which is of course the sort of main Eta Carina LBV, it had its giant eruption in 1843. And at that point, for 20 years long, it lost 1 solar mass every single year. Even now, we're 180 years later, and it's still losing 10 to the minus 2 solar masses per year. So these are extreme objects. This might have been a merger, so again, a binary product. For the Doradus ones as well, there's some new evidence or theories that they also might be products of binary interactions, but we will not look at that, and we will also not really focus on Eta Carina in this talk. We will mainly trying to look at Doradus LBVs. Now, so the main question that I'm trying to answer in this project, in this PhD project, is what happens to stellar envelopes and wind outflows when these stars enter now these regions in the Hertzsprung-Russell diagram where LBVs live. Because, like I said, there's a lot of unknowns. Even some of the basic parameters are not really sure. So there's really a lot of questions, and we don't really know what happens. But on the other hand, these stars are very important for the mass loss rates, for example. I've plotted here a plot of the age of the star, just as a 1D stellar model. It shows the age, and then on the y-axis the mass loss rate. And you can see in the main sequence it's very well behaved, and then you've got this giant peak, and this peak is the LBV stage. So yeah, something is happening here, and it's not really clear what, but yeah, it's a very important stage for the evolution of these stars. Now, perhaps more poignant for all of you listening here is, why do we care what happens to these stellar envelopes and outflows? So the reason, again, it's these mass loss rates, but the reason is that these mass loss rates today in, for example, 1D radiator transfer codes, which are used to infer all kinds of parameters from observations, and these all feed into stellar evolution, galactic evolution. They are very, very ad hoc. They're, some might say that some parts are basically just made up. There's not a lot of physical things going on there. They set them, and that's that. So yeah, that's of course that's a quite bleak view. But then in contrast, these sort of 2D RHD models, they can be used to predict stuff. And so we're not assuming things like we do in the 1D codes, where some people speak about a free parameter hell, because there's just so many free parameters you have to choose, and you have to try to produce something. That's all not necessary in these 2D models. So let's go to some of the basics of radiation-hydrodynamic simulations. And well, let's start at some math. It's unavoidable, I think, with these kinds of models, but I will be short with these. So yeah, things that we then solve for RHD are just mass, momentum, and energy conservation, which then makes it hydrodynamics. To make it radiation hydrodynamics, we have to, of course, add the radiation energy, which is the fourth equation, and then you need to still close this system of equations. So we add, for example, a gas energy equation. But from these equations, we can introduce a couple of very important, and I've called them key concepts. So for starters, with momentum conservation, you see this F graph and F rad, which are just gravitational and radiative force. Now, the Eddington factor, or this written by gamma, is defined by the radiative force divided by the gravitational force. So it's just the ratio of the radiation pushing outwards and the gravitation pulling, of course, matter inwards. And you can also write this parameter as you can see here, and it says there there's a stellar luminosity and a stellar mass. Now, if you fill in some normal values for the sun, you get a gamma of 3 times 10 to the minus 5. So it's, in the case of the sun, for example, really not important. You can really get away with using hydrodynamics and not including radiation hydrodynamics. However, if we then look at typical values for an LBV, where your mass projects to 50 solar masses and luminosity to 1 million solar luminosities, you can really quite quickly see that in this case, you get a gamma of like 0.6, and this is without ever even touching the kappa, which is the next key concept. This is called the opacity. For the opacity, we are using a hybrid opacity model, so-called, where we take both Rosseland mean and line opacity. Now, what are these? So opacities in general are a function of density and temperature. And so this Rosseland mean opacity works really well for a static medium. They're derived for a static medium. So this works in the optically thick parts of your atmosphere, so deep within the stellar interior. And you've got some opacity bumps, which are just they're related to the ionization stages of some species, for example, iron, helium, and hydrogen, where in a fairly narrow temperature range, your opacity just increases quite a lot. For example, the iron opacity bump, which is fairly important for these models, in general, your opacity just suddenly increases by a factor of 3. And you can also see it here. This is the iron opacity bump. It just increases in this yellow line. Now, outside of your photosphere, it falls off, and it's not that important. But yeah, of course, if you times it times 3, then this 0.6 from before now becomes 1.8. So you're actually exceeding your gravity by your radiation at this point. Now, this is not the only important opacity. You've also got line opacities, where you're considering the spectral lines. They, of course, can also block light. And especially in an accelerating medium, this gets Doppler shifted. And you can really cut out quite a big swath in frequency space, and this can have a profound effect as well on your total opacity. You can see it here with the blue line. It just shoots up as soon as you pass the photosphere. And this can drive a wind in itself, and then we call it a line-driven wind. Now, another concept relates to the energy transport. That was the radiation energy equation from before. You can rewrite this, simplify this a little bit by taking a 1D radial approach and just looking at steady state. But from this equation, we can introduce the next concept called photon tiring. Now, photon tiring is really just you take all of your radiation and you put it in lifting material from the star. So you put all of your radiation, radiative luminosities in to just drive mass away, meaning that the other energy forms don't really matter anymore, and then at infinity your velocity is just 0. And then you can rewrite this a little bit, and then you get this photon tiring parameter, which is just how much of your maximal masses you are now driving. A second concept here is convection, or better even enthalpy transport, which are these first two terms. And you've got gas enthalpy and radiation enthalpy. In this case, radiation enthalpy is, again, really, really important. Yeah, so this is just a whole nother a form of energy transport. So your star doesn't only need to look at radiation, but can also just basically form bubbles and then move them upwards. Now, I've told all this because I want to really bring across the fact that LBVs are a very special domain of massive stars. They're really not like the others. So I've written a lot of parameters for O stars, Wolf-Rayets, and as Doradus LBVs. For example, at the effective temperature, it's a bit lower than the O star and the Wolf-Rayet star. Massless rate is a bit higher than those two. But just looking at the physics, so the photon siring, for example, for an O star, this is not even a factor. It's really not. For the Wolf-Rayet star, it's a little bit higher, but still really not important. But for an LBV, this can become really, really huge, right? So it basically potential up to 1. And similarly for this enthalpy transport, I've then taken the enthalpy transport through the iron bump, because as you remember, here the opacity becomes really high, so your radiative force can become really high. And for an O star, at this point, only 15%, 15 to 20% of your energy can be transported using enthalpy. So most has to come through radiation. For Wolf-Rayet, it's even worse, but for LBVs, up to 90% or even higher of energy in this regime can be transported using enthalpy, which means that you've got a whole other different way of transporting energy through this iron opacity, the iron opacity bump, to not blow up your star, basically. Now let's also quickly look at what has been done before. So up until a decade ago, basically, computers were not powerful enough to really run multi-D simulations. But in 2018, there has been an LBV model, a 3D LBV model, RHD. This is the only other, in this paper, they're the only other LBV models in multi-D. So they really formed inspiration for what I'm doing now, but there's some big caveats. For example, they have no line opacity, which is it's a whole other opacity source that they do not have in this case, and also their massless rates are quite low for LBVs. Now, in our own group, we have done 2 recent simulations, both of O stars and of WR stars. And so it's in between these very exciting results and very exciting simulations that I am trying to bridge, which, as you might have guessed, is proving slightly more difficult than one naively would have thought, because it is such a different domain. So let's now go to the simulation setup. And again, to this question, what now happens when these stars enter these regions? Now, the problem is, and I also found this already in my master's thesis, is that these models are extremely sensitive to the lower boundary conditions. So what conditions you use can produce quite different results. And so to try and get some physically motivated lower boundary conditions, we turn to some stellar evolution code, MESA in this case, and we let a 60 solar mass star evolve. And in the end, it indeed crosses into the LBV region, as you can see here. Now the trouble is, MESA only produces the structure of the star up to the photosphere. And of course, I am also very interested in the outflow. So instead, I used a semi-analytic hydrostatic atmosphere model with then a wind on top. And I tried to basically stitch that one to some point within the stellar evolution model. And that then looks like this. So the blue curve is the stellar evolution model, and the yellow curve is the semi-analytic model that I'll be using as boundary conditions. And you can see there's a huge difference. Now, this mainly comes from the fact that in our 1D model, we're using a way more physical way to describe energy transport. So again, this is an example of this free parameter hell, where you just change this value and get a whole different result. Now, this also is a really nice example of these opacity bumps, in this case iron and helium, that change quite the structure quite dramatically. Yeah, you can see you could stitch these come to the same point, so you can just stitch them, and you have, in principle, have just one continuous model from the center to here. So what kind of parameters are we now speaking of? So I went down to a lower boundary temperature of 400,000 Kelvin. So this is chosen specifically so it's deep enough to be well below the iron opacity bump, which is at some 200,000 Kelvin. But of course not too deep. Now this temperature then corresponds to a radius of 38 solar radii. And yeah, at this point, the stellar model has lost 3 solar masses from the beginning, so we're still at 57. And then I place my box in this star. So I start at the 1 lower boundary radius, so that's also the unit of length in these simulations. So I start at 1 and then go out to 40 for a length of 1500 solar radii, and my box is 1 lower boundary radius across. And then yeah, I simulated this using MPI and Marvec, which is a code framework for solving these sort of RDG equations. So now let's look at these 2 LBV simulations and of course their implications. So what I'm going to show you now is a zoom in of the simulation. I zoom in from on the lower part, so from 1 to 10, and I've stacked it also 3 times on top of each other, so I have a little bit of a nicer aspect ratio. But I'm showing density in the colors, and then the arrows show the velocity. So I can start this, and immediately you can see that this inflates even more than before. And you can see a lot of turbulence occurring, and you can see this sort of breathing motion, so material being thrown upwards and then moving down again, and then moving back upwards. And then at this point, you just saw, after a while, suddenly a giant outburst occurs. And then it just goes all again. So for example, I think another outburst is coming. Now, just again, a lot of material being thrown upwards, being thrown out of the simulation domain, and just never coming down again. And then it just starts all over again. So yeah, I can let this run, but it will just it will look fairly similar as those other couple of loops, let's say. So to then analyze this a little bit better, I took these sort of snapshots, which are 2D. I then took a radial average, so I have just a 1D line from the lower boundary to the upper boundary. And then I stacked them all next to each other to create this sort of plot called we call it a space-time plot. Because on the x-axis, you can see the time in days. So this is the beginning of the simulation and goes to the end. And on the y-axis, you can see, in this case, the radial component, radial coordinates. And on the other hand, I took some average over the temperature, so you can later recognize the opacity bumps, because like I said, they happen at very specific temperatures. And so there's a couple of things that you can see. This is again the density. And in the beginning, there's this low density area, let's say, above the star itself. But then after a while, of course, you get this really big outburst. The entire simulation domain fills up with dense material. This becomes and remains optically thick for the entire time. And so it never really comes down again. Now, what is happening here is these arches at the bottom, they are storing mechanical energy. So they're given a lot of kinetic energy at a ion bump, thrown up, and then eventually they don't make it out. So this energy is still there, it's building up. And then after a while, you get these really, really big outbursts as a result. Now, however, and this is also a really instructive plot. This shows the velocity with blue going upwards and red going downwards. You can again see this line-driven wind because it's optically thin. This line driving is very efficient there. And you can see that there it goes fast, and during these couple of outbursts it also goes fast, but the material really slows down for all the rest. For example, at the top, you can see there's not a lot of really blue anymore. And it becomes even more clear if I divide all of this by the local escape speed to get this. So again, here blue is escaping and red is not. So you can see that although there's a lot of material moving out of my simulation, it is not actually going to escape. So in the end, it would fall back in the real star. Now this already poses a fairly big question, because like I said in the beginning, LBVs are known for their really high mass loss rates, and this seems to tell something else at this stage already. To get some sort of overview again, let's just look at these evolution of effective temperature, photospheric radius, and mass loss rate over the time. And you can very clearly see that in the beginning, your initial conditions start relaxing. And right in the beginning, you've got this steady line-driven wind with this mass loss rate of 10 to the minus 5, 10 to the minus 4 solar masses per year. But then after these outbursts happen, you see, well, this semi-periodic outburst of a lot of mass being ejected through the outer boundary, up to 0.1 solar masses per year instantaneous mass loss rates. And in these peaks, there's also a high degree of photon tiring. And so a lot of the radiative energy, several dozens percent and up to even like 50–60% of the energy is being put into driving this mass upwards. Another instructive plot, I think, is this one. This shows the opacity, so it's a total opacity, so both line and Rosseland mean opacities. And again, in the beginning, you clearly see this line-driven wind, really high line opacity. And this one is also fairly nice because at the bottom you can see the ion opacity bump. So this is then the Rosseland mean opacity that increases quite a lot. And you can see that it's fairly constant around this 200,000 Kelvin mark. But now, why is this mass all not escaping? Well, you can see this is all fairly dark. And if you remember, this radiative force is of course proportional to kappa, and if kappa is low, then well, there's not a lot of radiative force to drive your matter outwards. And this is because, for example, there you can really nicely see it becomes dark when it becomes too cold. So when your hydrogen can start recombining, you lose all of your opacity support. And so the material is just not being driven outwards any further. And so eventually you would expect it to fall down. but yeah, usually in 1D codes and so on, this wasn't really considered as up to now, as far as I know. Now, this is still a space-time plot. However, I've here changed the space coordinate to this x. So this is just a scaled radius. I've also put the corresponding radii here. So what this one does is it really stretches out the lower parts of the simulation domain, and it compresses the higher parts. You can also see that in the temperature on the right. And this is really stretched out. And what is shown here is, well, it's written convective flux divided by radiative diffusive flux. Perhaps a better way to call this is enthalpy transport over radiation transport. So green means that enthalpy is very efficient, whereas purple means that radiation is efficient. And you can immediately see there's a lot of green here. And so, like I said in the beginning already, this is very, very different from O stars and WR stars. We do not see this here. Now, this entire thing is the iron opacity bump, and like I already said at the beginning, at this point, your kappa becomes so high that if it did not change, you would just start blowing a wind from there, like what happens with Wolf-Rayet stars. But in this case, you can actually convert this energy to convective, to enthalpy transport. You can transport it using enthalpy. Yeah, and also in the top part, we are still optically thick. So even though we're still very deep within the atmosphere, we are not still using this enthalpy transport. We are here radiatively transporting all of our energy. Now, so this all this all shows that there's, because so I start this how to say this? Well, the initial conditions from this simulation that I just showed you were taken straight from some 1D evolutionary code, right? But if I put it in RHD, you can see there's a lot of inflation happening. And this tells us something. This tells us that we're basically just pumping in too much energy. Our lower boundary temperature is too high to actually create a stable star. And so there's too much temperature there, which corresponds, of course, to a too high luminosity. So too much, yeah, it's just too much energy, which then has as a result this really big inflation. Now, that's of course a bit of a problem, because at this point, if you would compare these, for example, the mass loss rate of 0.1 solar masses per year to what you would expect, it's way higher. It's definitely not an S Doradus in its quiescent phase, which is, well, that was the initial condition that we put in, according to MESA then again. It's definitely not that. It's even too high for an S Doradus in an outburst phase. It comes closer to, for example, the giant eruptions of Eta Carina. But then, of course, this matter is not really escaping, so it might produce these really big inflated clouds, but it's of course not really sure at this point. You could even try argue about this being more in the direction of like supernova impulsors, which are these really bright events that you can see on extragalactic distances, which, as far as I know, is also not really known what drives them. But again, these are very energetic events. So yeah, there's a lot too much energy being pumped in here, and to try and decrease the amount of energy in the simulation, I tried then lowering the lower boundary temperature by 5%. So 38,000 Kelvin instead of this 40,000 Kelvin. So yeah, that's not a lot, of course. And I needed to do this manually, just run a new simulation setup with everything else the same. So the same lower boundary radius, density, the same mass, the same sort of domain, only changing the lower boundary temperature, because we have no feedback from the to the lower boundary. So manually set, and then the difference between the last simulation and this one, I will now show. It is striking. So this is again density, and you can see the sort of the same breathing motions of this material being thrown upwards, but apart from that, it's completely different. So this simulation simulates the same time, so it goes to 550 days, more or less, at the same time as before. But now, of course, we don't have these really big outbursts. Our energy buildup is nowhere near great enough to trigger these huge outflows. We've got a line-driven wind through the entire time, so the entire top part stays optically thin, line driving stays efficient. So it is like I said, a striking difference for this fairly low, fairly small difference between this one and the next one. This can also be shown in the velocity plot. So again, like before, blue means going upwards and red means going downwards. And again, in this one, you can also see that after the initial relaxation, you can see that there's the wind slows down a little bit, but it's still going up. It's still escaping. There is perhaps a slight evolution, which you can also see, for example, here. This is again the overview. And you can see that after you've got the first relaxation, of course, in the beginning, which takes basically the same time as before. You can see there is no or very slow evolution. I, of course, do not know how this goes on at this point. These plots I've produced in the beginning of this week, so it's very still ongoing research. So yeah, you can see this is a very, very slow evolution, and that even in itself doesn't really need to be a problem because, of course, these Doradus LBVs, they do evolve at the timescales of several years to decades. And this time here, it corresponds to 1.5 years already. So to make the contrast even more striking, let's just put next to it the last one. Yeah, the axes are not the same for both, but for example, for the massless rate, I've made the same dotted line in both. So yeah, there's a huge difference between these two, even though there's a very small difference in the lower boundary temperature. So, like I said, this is still ongoing, but sort of the main takeaways I want to give you from this presentation is first that these slight variations in conditions lead to very, very different characteristics of the envelope and the wind. At this point, this seems to be qualitatively consistent with the behavior that LBVs indeed show. And with the quiescent phase and then the outburst phase, or probably this is bigger than the outburst phase, but then it's again just tuning of lower boundary temperatures. Second is the fact that LBVs are very different stars from O stars and Wolf-Rayet stars. They are all, of course, massive stars. In the classic view, they are evolutionary. They go through all these stages, but they live in a very, very different domain, a very different parameter space than these other stars. As a big example for this is very efficient radiation enthalpy transport throughout the iron bump region, which you do not see at all in these other stars. And now a big question really is the fact that the high amounts of matter moving upwards, especially in the 400,000 simulation, well, at one point it will fall back. And that really calls into question another assumption of these 1D codes, where they assume a smooth outflowing wind. And these sort of codes are then, of course, used to infer all kinds of parameters from observation. and that then again feeds into stellar evolution and galactic evolution and the like. So yeah, huge question there. Now, as far as future work, there's, like I said, there's no feedback to the underlying stellar core. So if we pump too much energy, we're just setting it at this and it's just creating a sort of hot plate. But this is something that we will be working on in the near to far future. Something else would be to have some spectral synthesis of these models to really see how these would look like if you were observing them, see if we can then match them to actually observed features. And then this is also ongoing work. And yeah, just in the end, these mass loss rates that you would derive from the spectra, would it actually mean that they actually escape the star? Because from these simulations, it doesn't look like at this point. But that then is an whole other kind of worms. If the mass doesn't escape, you still need to go from O stars to WR stars, and the mass needs to be stripped somehow. So perhaps a binary interaction or so, but this is again something, some big questions. But yeah, that was it. Thanks all for your attention, and then I will take any questions you have.
Thank you very much, Pieter, for walking us through your research like this. It was great talk. I, of course, have questions, but I might leave the audience a chance to start. If someone has one, please raise your hand, maybe with the react emojis if you do. Else I can break the ice, no problem. Oh, we have someone. I don't see who, but go ahead. Oh, Nicole.
Hi, Pieter.
Hi.
So do you think, so do I understand that you just calculated these two simulations, or do you have others?
Well, I have calculated some others. I've went down to 360,000.
Okay, that was my question.
Yeah.
Are you just happened to cross some sort of threshold with 400,000 and just decreasing it by, I think it was 5%, just made you change so much? Or do you believe that, you know, it's linear or something like that? If you would increase it to 420, would you get even bigger outbursts?
I have made 360, so I've decreased from the beginning simulation 10%, and I've also increased it 10%. So the decreasing at 10% made it a very well-behaved star. Basically no inflation, nothing really happening. Increasing 10%, you basically didn't have a star left, because from the bottom you were just shooting out so much mass, basically going super Eddington from right at the bottom. So yeah, there is a threshold, and there is a very sensitive regime here, but I think it is rather physical and not. Yeah.
What makes this so sensitive? Is this accumulation, this hot plate you're talking about?
I'm not really sure. This hot plate, of course, well, it makes this, well, like you said, it accumulates energy, so after a while it just needs to come out. But yeah, as to what makes it so sensitive, I would just think the fact that we have, so there's a lot of radiation. These are very inflated stars to begin with. So you're fairly close to the Eddington limit to start with. So you start with like 0.5, even if a fairly well-behaved star. So you really don't need a lot anymore to start inflating massively.
It's very close to instability. Okay, thank you.
Laura, je vois que tu as la main levée.
Yes, thank you very much, Pieter, for your talk. I wanted to know, perhaps you've answered this question slightly before, but what happens to stars like, for example, P Cygni, who has erupted like 4 centuries ago, but it essentially does nothing. It has done nothing for the past 4 centuries. So what actually makes this star stable during such a long period?
Yeah, so I don't really know, right? It's all very much still ongoing. I know that P Cygnius is considered an LBV by most, like a more one-off, so a giant eruption one. I am not sure why it would be stable. Maybe it was indeed a binary interaction thing where it just got dumped a lot of energy, perhaps some merger, like Eta Carina is being thought at this point. And then, yeah, if the energy is then thrown outwards, your energy is used up. So yeah, you go back to being stable. But yeah, the physical reason behind why for the Doradus stars move, why the Eta Carina blow up, I cannot answer at this point. So the simulations are trying to explore what's happening physically within the envelope and the outflows. So what you could see, but deeper down we don't model. We don't have the capacity to do that at this point. So yeah, that's an open question.
Thank you.
Maybe I'll go in with one of mine.
Go ahead.
In your new simulations, we see that at the end you start to have some increase, some massless bumps in your plots that you were showing, but the time stops at roughly 500 days. I see. Would you expect to see, or on your leftward plots or with your new models, would you expect that if you let those simulations run a bit longer, that you'd eventually get this buildup of mechanical energy that would maybe lead to a major outburst and then go back to some sort of quiescent phase, a bit like what Laurent just described?
So as you can see, this last change in photospheric radius seems to be a little bit bigger. Now, of course, like I said, these models, I made these plots literally the beginning of this week, so I do not know if this is just a unusually big one or if we will evolve slightly further. I think that it will keep evolving slowly, and that indeed eventually we will fill up the entire domain. But I don't know. This is more of a gut feeling. This is what I think at this point. And yeah, for timescales, it will probably be then not 500, but maybe 5,000 years, 5,000 days before this happens. But yeah.
Because if I may, it's looking at those two plots, this is great actually that you show them together like this. You could, guess you see maybe some kind of scale invariance, namely that your plots on the lower left column looks really like the beginning of the lower right plot, where you have these initial bumps, then some sort of stabilization for a while, and then eventually you get those massive outbursts. So so for the simulation domain also, I was going to say that maybe if you let for the one at 400 kilokelvins, if you would extend it further, maybe you'd see material coming backward, and then you have more accumulation of energy. But I'm especially to highlight this kind of scale invariance in your models that would appear to be there with those initial simulations.
It does at this point. Yeah, that's a really nice observation. It does look that way. I can, of course, not comment at this point. But yeah, if it does, it would be very nice, right? Because then you have a fairly nice way to just go from this quiescent phase to a more outburst phase. And in this case, the 400 is too extreme. But yeah, by very slight changes in the lower boundary temperature, then in this case, so the lower boundary energy coming in, because this presents. It's a 20% increase, more or less, in luminosity. So that's not that much, right? All in all. So if it indeed would evolve to if the left one would evolve to the right one, would be very nice. But yeah, that's for later at this point.
Yeah, and including the feedback would probably do something like that, where would change the temperature at the lower boundary condition, and then maybe put it. Heightening it, lowering it, so you'd probably get these different behaviors in one kind of model.
For example.
Very, very eager to see where your work leads, Pieter.
Thank you.
So we would have time maybe for another question if someone has one. Else, we can thank our speaker again. Thank you a lot, Peter, for taking the time to
My pleasure.
put this together. And you said it's results you got last week also. So it's very nice and very cutting edge work that you're doing.